Okay, starting to this class. In our very last class, we actually started a small portion about the elasticity chapter. This is the first chapter of our second booklet, chapter number 5. In elasticity and Young's modulus, we have these definitions: deformation, elastic deformation, and then we can have plastic or permanent deformation. So any deformation that is reversible, that we call reversible elastic deformation. Any deformation that is not reversible or permanent, that's what we call plastic deformation. So then we have this thing that when a load is the elastic deformation is defined like this: the deformation is reversible when load or deforming force is removed, object gets back to its original dimensions. So shape, size, length, width সবগুলাই properly আবার gain back করবে, সেটাকে আমরা বলতেছি elastic deformation. Then it says irreversible or permanent deformation: when the load is removed, object does not get back to its original dimension when plastic deformation happens. Particles of one object move permanently or displace with respect to each other. This displacement is done by the load. The amount of work done to make plastic deformation is stored within the object as elastic potential or strain energy, which means whenever any object will undergo permanent deformation or plastic deformation, মনে করো হচ্ছে একটা অবজেক্টকে আমরা টান দিয়ে পার্মানেন্টলি লম্বা করলাম, so it is remaining that dimension. It means some work had to be done to move the particles of those objects from their original position to a new permanent position. That is basically mass moved in a certain direction. So the amount of work that we have to do to make that possible is basically what's the amount of energy that we have to spend to make that deformation possible, and that amount of energy will be stored within the object as deformation energy, or sometimes we call it strain energy. Then we have the Hooke's law. Hooke's law is given by F equals to kx. F is the external force causing deformation. Whenever we are gonna use, so what is given over here, have a look. F equals to kx, whenever we use the vector sign, this is perfectly all right. F equals to kx when F is the external force causing the deformation. Whenever we are considering the external force, in that case, the direction of F and the direction of deformation, they're both same. That's why there is the minus sign over here. But if we use minus F equals to kx, have a look. This F is the elastic force from within the object to resist deformation. This is a part that you need to understand, that whenever we will apply some force on an object for deformation, the object, because of its elastic properties, the object will resist that deformation, which means the object from within itself will produce a certain force to oppose that deformation that we are trying to cause to the object. So if we consider that force and work done by that force, that would be and if we want to write the elastic formula for that force, that would be as a vector quantity, that would be given as minus F into k into x. এখানে f এর উপর একটা ভেক্টর সাইন হবে, এই ভেক্টর সাইনটা সামহাও এখানে পড়ে না, এটা একটু দিয়ে নাও. There should be a vector sign over here. I might as well also
sir second স্যার আপনি দিয়েছেন স্যার?
বলো
স্যার আপনি কি সেকেন্ড বুকলেট দিয়ে দিয়েছেন স্যার?
না, সেকেন্ড বুকলেট কালকে থেকে কালেক্ট করতে পারবা, আমি জাস্ট নোটসটা পড়াচ্ছি.
মানে স্যার আপনি যে বললেন যে এটা দিয়ে দাও স্যার.
আচ্ছা, that was reflex.
স্যার নেগেটিভ কেন হবে এটা একটু বুঝাবেন, আবার বুঝতে পারলাম না.
অবজেক্টে যে ডিরেকশনে আমরা ডিফর্মেশন করতেছি, অবজেক্টের ভেতরে within the object the opposing force will work in the opposite direction of the deformation. So if you're trying to elongate an object, the object will try not to get elongated. So deformation x এর যে ডিরেকশনে কাজ করবে, অবজেক্টের within the object the inherent force that opposes the deformation will work in the opposite direction of the deformation. এখানে মার্ক করার জায়গাটা কইতে পাই, এটা দেখানো পাইছি.
x কি length?
X in this case represents deformation.
Okay.
Why can't I simply make a single line over here? All right, that's better. And yes, so if it goes to kx, এখানে f টাও একটা ভেক্টর কোয়ান্টিটি, সো এটা হচ্ছে আমাদের ডিফর্মেশন ফোর্সের জন্য আমরা যদি অ্যাপ্লাই করি তাহলে সেই জিনিসটা আসবে. And then we have the graph of elastic graph, f into x graph. This is drawn for a straight line which is representing the deformation is only represented for the elastic region of the deformation. So for that region, the force versus the extension graph will be a straight line that passes through the origin. The gradient of the graph is given as the m equals to k. K in this case is the constant of that thing. And then we can find out the EP stored. EP stands for elastic potential energy. EP stored within the specimen is equal to the area under the fx graph. So area between the force and the extension graph. So area should be adjacent to the deformation axis. This is really important কারণ এটা পরে আমাদের একটা certain type of mathematics এর জন্য কাজে আসবে, সেটা আমি একটু পরে দেখাচ্ছি। So EP stored is given by area under the fx graph. So E equals to W equals to half fx. This is basically a triangle. So equals to half into kx into x equals to half kx squared. So this is the expression that we use to calculate the amount of energy stored within a specimen. One other type of graph that we can also have is whenever we have a force versus distance graph or force versus length graph. সেটা আমি একটু দেখাচ্ছি। In some cases,
স্যার মিউট হয়ে গেছে স্যার।
এই গ্রাফগুলো একটু দেখো, দেখে বোঝার চেষ্টা করো যে আমি শেডের এরিয়া দিয়ে তোমাদের কি বোঝানোর চেষ্টা করতেছি। Have a look. Here, each of the shaded area equals to energy stored. So if we have a graph of force versus length of the object, then the graph would not start from the origin, because this intercept part over here, this is basically represents the object's original length or unstretched length. So before deformation, this is the length that the object starts with. So when no force, no deforming force is applied, then the object still has some initial length to start with. That is this length. And then as the length of the object starts to increase, or the object starts to undergo deformation, so as the applied force gets slowly bigger, then the object is going to start to get bigger length. This is a graph drawn for an extension scenario. Extension means that the object is being elongated. But in other cases, we can also have for a compression scenario. Compression scenarios graphs would simply have the length of the object slowly becoming less. So if we have compression scenario, let me try to draw that with blue maybe. So let's say if we have a spring that has some long length and we apply some compressive load or squeeze the spring, in that case, the length versus force versus length graph can actually look somewhat like this. So it's going to be straight line up to the elastic limit, and then the length is going to become asymptote on the y-axis, because we can never actually make the object have zero length. That's not going to work out. So that is for the compression case. In this case, we can easily calculate the energy stored within the elastic range by finding out the area under the triangle. But if you have to go for the finding out the area that is stored under the curve, we need some sort of square counting, or we'll need some sort of integration formula to be used, which is not included in your syllabus, but just saying that this is the part that we're going to require for compression cases. So if it's a compression scenario, then the length of the object can become less than original length. So in this case, this much is the original length, and compressive load was causing the object's length to become smaller. So it was checked apart. The next thing that is important for your syllabus,
এই লাস্ট পার্টটা স্যার বুঝি না স্যার।
বলো কি বুঝো নাই?
মানে স্যার কম্প্রেশন লেন্থ আপনার কি বলেন স্যার, এটা ক্যাচ করতে পারছি না স্যার। With the blue diagram, sir.
If we apply extensive load or tension on an object, for example, let's say you have a spring that is attached over here. If we apply a force that is going to make the object longer, then we're going to have this graph. If we have a scenario where we apply some load on the object to make the length smaller, then we're going to have this graph.
Okay, sir. Thank you, sir.
বুঝছো কি? So this is the original
Yes, sir.
length for the extension scenario, and then as we slowly start to apply bigger and bigger force on the object's length is going to slowly become bigger and bigger and bigger from the original length. Whereas for the compression case, we have an initial length to begin with, and then the length is slowly going to become smaller. Just hold on a bit. I have a delivery to receive. So one more thing that is important, that whenever we are going to have the force versus the extension graph or the force versus length graph, the area under the that is adjacent to the length axis or adjacent to the deformation axis is going to give us the energy under the stored within the graph. This is important because sometimes they actually give this kind of graphs and they label a different type of rectangles or trapeziums over here and asks you to find out, in mostly in MCQ cases, that which of these geometric region represents the energy stored within the specimen. So you have to be careful to choose the area that lies between the graph and adjacent with the length axis, not with the force axis. এটা এই জন্য ইম্পর্টেন্ট, দেখো একটা জিনিস খেয়াল করো, ফোর্স ভার্সেস এক্সটেনশন গ্রাফের জন্য ফর এ স্ট্রেট লাইন দ্যাট passes to the origin, honestly speaking, because this is a perfectly straight line, if I try to draw this area right over here, let me draw that with a different color, maybe with green. If I try to draw this area geometrically, এই area আর এই area টুকু exactly equal হবে, তাই না? Don't understand, because this is a rectangle and this is a diagonal, so there is no mathematical difference between the area calculation of these two parts. There is none. So mathematically তুমি এই area calculate করো, তাও energy stored within the graph within a specimen পাবা, এটা calculate করলে পাবা. But if it is a force versus length graph, then that's not gonna be the case. You have to be careful to measure that from the point the object starts deforming and for the ongoing deformation process. So either from the original length for an increased length scenario or from the original length to towards a decreasing length scenario, that's where the energy gets stored. So that's why it's important that you understand that energy should be calculated using the adjacent side, that is adjacent with the length axis or the deformation axis, not with the force axis. So এই diagramের জন্য আমাদের calculation usually error হয় না, because both the areas are exactly equal. But whenever we will be provided with some sort of force versus length graph, then we really have to be careful to carefully calculate those numbers. এই পার্টটা বুঝা গেছে কি everyone?
Yes, sir.
Energy should be calculated with the
স্যার নাম্বার একটা বুঝলাম না
adjacent
স্যার
one.
স্যার
আচ্ছা, একজন করে। হ্যাঁ, ইউসুফ বলো।
Sir, energy should be calculated with the adjacent topical side, কি বলেন স্যার?
Energy should be calculated for the area that is adjacent with the length axis or the deformation axis, not with the force axis.
Okay, sir. Thank you, sir.
মুনাম কি বলছো?
স্যার থার্ড গ্রাফটা বুঝলাম না, এটা কি করলেন আপনি?
এই গ্রাফটা?
জি স্যার।
এই দুটো গ্রাফ exactly same. There is no difference in these two graphs, only the axes are flipped. একটা হচ্ছে force versus extension, আর একটা হচ্ছে extension versus force. গ্রাফ দুইভাবে আসতে পারে।
আর দুটোই কি আমরা এই যে এক্স অ্যাক্সিস এর সাথে আসলে এটা নিব?
হ্যাঁ, এনার্জি স্টোর উইদিন দ্য স্পেসিমেন ক্যালকুলেট করার জন্য আমাদেরকে ডিফর্মেশন এক্সিস এর সাথে অ্যাডজেসেন্ট এরিয়াটুকু ক্যালকুলেট করা লাগবে, ফোর্স এক্সিস এর সাথে না।
কেন স্যার এটা?
Because the force can be zero and the length can still have some value. The deformation gets started when the object starts to have change of its length, not exclusively when the force starts to become more than zero.
ওকে স্যার, বুঝতে পারছি।
length non-zero value তো আমাদের force value zero হতে পারে, that is applicable for the force versus length axis. এই গ্রাফের জন্য জিওমেট্রিক এরিয়া হিসেবে তোমার এই এরিয়া দুটো এক্স্যাক্টলি ইকুয়াল, সো এখানে ক্যালকুলেশন করলে ভুল আসবে না। But ideologically, this is basically the area that represents the stored energy stored within the specimen that lies between the graph and the deformation axis.
বুঝতে পারছি স্যার।
আর কেউ বলছিল কিছু একটা? Anyone else? আচ্ছা, এইটা গেল। এরপর ডেফিনেশন আমাদের যে নতুন কম্পোনেন্ট গুলো আসবে, এটুকু মনে হচ্ছে আমাদের গ্রাফ। সো these are labeled over here as traps. So because this is the part where the students might make mistakes, the students over here actually just labeled the necessary parts, didn't write any description because they didn't feel like it, which is perfectly all right, because you do understand you have to be careful about these things. Then we have the new parts that is in our AS syllabus, which is called stress. This is actually sigma. Big sigma looks like this without the tail. Sorry. So sigma looks like this. Yes.
স্যার এই বুকলেটে ডিস্ট্রিবিউট করা হয়েছিল?
না, এটা কালকে থেকে গিয়ে কালেক্ট করতে পারবা, এটা প্রিন্ট করা হয়ে গেছে। Stress is given by force per unit area, normal cross sectional area stress. So this is given by force by area, scalar unit into per meter square. By definition, this F is not the applied force, rather it is the applied sorry, এখানে একটা জিনিস একটু ভুল আছে. I might actually cross this out. Okay, rather it's the elastic force from within the object that raises the deformation. Pressure, on the other hand, is defined as force by area, where the pressure equation of force হচ্ছে external force. So difference একটু বুঝো. Sigma stress equals to force by area. By definition, এই ফোর্সটা হচ্ছে elastic force that is resisting the deformation. Pressure equals to force by area. এই F টা হচ্ছে external force that is causing the deformation. They are practically both exactly same because of Newton's third law. By numerical value, applied force is equal to resistive force because each force has an equal and opposite reaction. So by numerical comparison, the applied force and the deformation resistive force or elastic force from within the object, they are both equal in number, but they don't work in the same direction. Applied force tries to deform the object, whereas the resistive force or the elastic force tries to resist that deformation, and it only exists as long as the applied force exists because of Newton's third law. So numerically they are both exactly equal, but definition wise they are somewhat different. So because they are numerically equal, so during experiments sigma equals to F by A is often calculated. So যখন আমরা experiment করি, so in many cases we don't bother to calculate or find out the internal force individually by its own location. Rather, the applied force or the external force is in many cases used to calculate the value of the force. যেমন এটা একটা experiment তোমাদেরকে আমি একটু পরে দেখাচ্ছি, experimental setup-টা দেখাবো. For example, P equals to F by A, which is called the external force. So during this explanation, এরপর আছে হচ্ছে আমাদের strain এর definition. Strain is given by delta. এটা হচ্ছে বাংলা লেটার থয়ের মতো দেখতে. This is the small delta. The capital letter delta is this one. The triangle is the capital delta, and the small delta somewhat looks like this. So extension or deformation on unit length or unit dimension. If by applying a force on an object by extension E, which had original length of L, then extension is given by E by L. So এটা হচ্ছে এটা qualitatively the strain quantity means by what proportion the object was deformed. Then comes the constant Young's modulus. এখানে Young's modulus এর উপরে ড্যাশ লেখা আছে, within limit of proportionality এই জিনিস লেখা আছে। এটা কারণ হচ্ছে স্টুডেন্টরা এই পার্টটুকু লিখতে ভুলে যায়। This is very important. Young's modulus is the ratio of stress and strain within the limit of proportionality for an object. So what I'm trying to say is that if you plot a graph of stress versus strain for an object, the ratio of strain versus strain, or the gradient of the graph of stress versus strain, for example, if I try to draw over here, let's see, if we draw a graph for an object that is stress versus strain, then for within the elastic limit or within the proportionality limit, what is the difference between elastic limit and the proportional limit? I'm going to talk about that just after a while. It's going to be part of our discussion. For the time being, let's say within the linear part of the graph, let me just put it that way. So within the proportionality limit, the line is going to be perfect straight line. When the proportionality limit is crossed, then the line is going to start to curve. So different objects can have different type of curves depending upon brittle substances, malleable substances, polymeric substances. We can have different type of curvatures. Young's modulus is the gradient of stress strain graph within the linear part of the stress strain graph. So we say that is within the limit of proportionality, that is within the straight line part of the gradient. So if we have the gradient of this much segment, that is basically what we define as Young's modulus. So by definition, Young's modulus is given by sigma over delta within the limit of proportionality or for the linear part of the graph. And then if we replace the values over here, we're going to get F divided by A on top. And over here, we're going to have extension E over original length, let's say small l. So this is going to be equal to FL divided by AE. এটা হচ্ছে আমাদের Young's modulus এর basic representation. Now there is a catch. Catchটা হচ্ছে, আচ্ছা, before I go for the catch, এই definition টুকু বুঝা গেছে কিনা?
জি স্যার বোঝা গেছে।
সো এখানে একটা জিনিস খেয়াল করে, এখানে ড্যাশ দিয়ে একটা জিনিস লেখা আছে, দিস পার্ট ইজ অনলি রিটেন ইন দিস ফরম্যাট টু হাইলাইট নট টু ফরগেট দিস ইনফরমেশন। স্টুডেন্টরা খুব কমনলি এই ইনফরমেশনটুকু ডেফিনিশন লেখার সময় ভুলে যায়, যে কারণে তাদের মার্ক লুজ হয়। সো ইট ইজ a ratio of stress and strain of an object within the limit of proportionality. It is, and also one more thing is important, that Young's modulus is the property of the material of the object. So it is not a specimen dependent property. It is a property that is similar to density. It is a property similar to specific heat capacity. So if multiple objects are made up with the same material and they are kept at the same temperature, which is very important, and as no matter irrespective of the dimension or shape, they are all going to have the same Young's modulus. So if we have, let's say, objects of different dimension, some are long, some are small, objects of different shapes, some are cylindrical, some are spherical, some are cuboid shape, doesn't matter. As long as all of them are made from the same material, they're going to have the exactly same Young's modulus. Young's modulus is a property of the material of the object, which is really, really important not to mess up with. আচ্ছা, এখানে ফর এস লেভেল উই এরপরে কিছু জিনিসপত্র লেখা বাকি আছে। এখানে কি বাকি আছে সেই জিনিস তোমাদের সাথে আলাপ করতেছি। আচ্ছা, এখানে একটা ইম্পর্টেন্ট ইনফরমেশন হচ্ছে, একটা জিনিস আমি তোমাদেরকে এঁকে দেখাই। Let's say we have a metallic specimen that looks like this. So I'm only showing you the face of the object. So this is the one side view. Let's say this top side is clamped with a vertical support system. So it is strongly clamped over here. So I'm just going to label this as clamp. And we are applying some load on the lower side with a second clamp, let's say. So let's say we have another clamp over here. It's pretty tight. And we have some load applying mechanism. So let's say this is a hollow space. So যেখানে আমরা আস্তে আস্তে লোড দিব, লোড দিলে এই অবজেক্ট আস্তে আস্তে লঙ্গার হবে। Now, what is obviously true? What is obviously true that as the object is going to become longer, it should definitely become thinner, because the total volume of the object V is going to be constant. So volume is given by cross-sectional area into length. So if the length of the object is going to get bigger, obviously the cross-sectional area should go down by the exact same proportion. Is it not correct?
Yes sir, you are correct.
Yes, sir.
ঠিক আছে, এটা হওয়া উচিত। তোমাদের সিলেবাস ভলিউমের জন্য, just to avoid complexity of calculation, we are going to consider that for our applied scenarios, the cross-sectional area of the object is going to remain constant. Now this might appear to be a bit too simpler, but that's the way your syllabus is designed, that we are going to consider, for the sake of simplicity, that the object is going to extend by length, but the change of cross-sectional area is not going to be there, or for our scenarios, the change of cross-sectional area is going to be negligible. In true case, it is actually not negligible. There is a whole theoretical property that goes around this idea that cross-sectional area would be changed, which is called Poisson's ratio. But তোমাদের সিলেবাসে এই জিনিসটা ইনক্লুড করা নাই। সো আমরা তোমাদের সিলেবাসের জন্য এই জিনিসটা নিয়ে আলাপ করতেছি না। আমাদের নতুন সিলেবাসে Poisson's ratio ইনক্লুড করা নাই। So we're going to consider that the cross-sectional area of the object is going to remain constant. Just give me a bit of a time. I'm going to look up in the syllabus to see whether they actually include in the very recent syllabus or not. Give me a bit of a moment. So we're full of the same syllabus. That is, this is for the syllabus for examiners who's going to sit for the LFSSM in 2022 and 2024. So here we have stress strain. Understand the deformation is caused by tensile or compressive forces. Forces and deformations will be assumed to be in one dimension only. AJ. Force and deformations will be assumed to be in one dimension, which means we are only going to consider the change of length. We're not going to consider the change of cross-sectional area. So we are only considering one-dimensional deformation. Understand and use the term load, extension, compression, and limit of proportionality. এগুলো আমি বুঝাচ্ছি একটু, limit of proportionality কি জিনিস একটু পরে দেখাচ্ছি। Recall and use Hooke's law. Recall and use the formula for the spring constant K equals to F by X. Define and use the term stress, strain, and Young's modulus. Describe an experiment to determine the Young's modulus of a metal in the form of a wire. এটা আমি একটু পরে দেখাচ্ছি। Elastic and plastic behavior. Understand the use of the term elastic deformation, plastic deformation, and elastic limit. Understand that the area under the force extension graph represents work done or energy stored for that matters. Determine the elastic potential energy of a material deformed within its limit of proportionality from the area under the force extension graph, which we just discussed a little bit earlier. Recall and use the expression EP equals to half Fx equals to half kx square for a material deformed within its limit of proportionality. So আমাদের actually area change এর পার্টটুকু সিলেবাসে ইনক্লুড করা নাই, সো এটা নিয়ে আমরা বদার শুরু করব না, so we're not going to get through that problem. We're just going to see this one. So this is the so we're going to consider the cross-sectional area for the object to be pretty much constant, which basically brings about the idea that if I write up this equation of Young's modulus over here, let's say y equals to FL divided by AE, we are considering that A is a constant. For our syllabus content, we are considering that L is a constant. A is a constant, and this L of over here represents the initial length of the object. Initial length means undeformed length of the object. So when we applied zero force on the specimen, how much was the original length to begin with? So L for a specific experiment is usually also a constant. It is not an universal constant. This is just a constant that is going to be considered to be constant because this is the starting value of L, which is not going to be varied over the experiment. The instantaneous length for the object changes, but the original length remains the original length no matter how much force we apply on the specimen. Original length means the unextended length, undeformed length. So L is also a constant, A is also a constant, which basically brings us that I can actually write that Y is equals to sum L divided by L divided by A multiplied by F divided by E. So this thing is practically represents a certain amount of constant because L is also constant, A is also constant. So I can write over here some sort of constant multiplied by F into E. The reason I'm trying to show you this graph is for one reason, is that you can have a look over here that Y is actually now for your syllabus volume is represented as some sort of constant multiplied by the F by E ratio. This brings us to the idea that if we are going to draw a graph of force versus extension for a specific object, that graph, and if you are going to try to draw a graph of stress versus strain for an object, that graph, these two graphs would have the exact same shape, where this graph is going to be constant, this constant times bigger in terms of y-axis. So let's see if this constant value is, let's say 2, then if this graph look like this graph is going to be just double the gradient of this one. If this graph has a shape like this is going to have the exact same shape up over the next part. You're going to have the same shape of force versus extension graph and stress versus strain graph considering your syllabus volume, because we are considering the cross-sectional area to be constant. এই কনসেপ্টটা বুঝা গেছে কিনা?
স্যার সেম শেপ কেন স্যার একটু বুঝবেন আমাকে স্যার?
কোনটা
সেম শেপ কেন স্যার?
সেম শেপ হওয়ার কারণ হচ্ছে বলতেছি, মনে করো একটা গ্রাফ হচ্ছে y equals to x square, এই গ্রাফের শেপ কেমন হবে? ইনক্রিজিং গ্রেডিয়েন্ট, তাই না?
ইয়েস স্যার।
একটা আরেকটা গ্রাফ যদি হয় এরকম, লেটস সে y equals to 2x square, এই গ্রাফের শেপ কেমন হবে?
Same, but probably a bit of change in the slope, sir.
This graph is simply gonna have double the y-axis value for all the possible x-axis value of this one. So এখানে যখন x equals to 1, তখন এই ব্লু গ্রাফের জন্য কোঅর্ডিনেট হচ্ছে এখানে 1, বাট গ্রিন গ্রাফের জন্য কোঅর্ডিনেট হবে 2, তাই না? This green graph is gonna have double the y-axis value compared to all the y-axis values of the blue graph for the same x-axis value, ঠিক না?
Yes, sir.
তাহলে তোমার শেপ সেম থাকতেছে। Simply the graph is becoming a bit multiplied by a constant factor, but if it is going up, or for this graph should also be going up. If this graph is going down, this graph should also be going down. It's going to have the same type of change, but the amount of change would simply be double. That's why we're saying the shape of the graph would be exactly same. The type
Okay.
of variations would be exactly identical. বুঝা গেছে?
Yes, sir.
আচ্ছা ঠিক আছে। সো এটা গেল আরেকটা জিনিস। আচ্ছা এরপর আমরা জিনিসটা দেখব সেটা হচ্ছে there is a certain experiment regarding the finding of the Young's modulus. So let me just find out a simulation for this.
Sir, O physics এ পাওয়া যাবে না স্যার?
দেখতেছি। কি আছে? Just a second. So we have this and this. দাঁড়াও ও ফিজিক্সে খুঁজে দেখি। This is not O physics. Where's light EM rotation of fluids, modern cardinal design tools, fun stuff, forces, conical pendulums, kinematics, forces. Light. Electricity, magnetism, rotation. না এখানে নাই। So this is actually done by Sarlis experiment. তোমাদের Sarlis experiment actually পড়ে তোমাদের সিলেবাসে নাই, so this is not the figure that I'm trying to go for. I would like to go for this method. Acha, I'm gonna pull up this experiment over here that is from YouTube and that is about 7.7:51. I'm gonna start make you see this thing. I'm gonna pause the recording for the duration and then I'm gonna start going through the individual parts of the experiment part by part. So let's have a look at this one. আমি একটা করে বুঝাচ্ছি। I'm gonna take this image for discussion over here. I'm gonna go through the piece by piece. So এটা হচ্ছে আমাদের typical experimental setup diagram. Try to understand. There is an additional safety class level over here because this is important that we use a safety class for this experiment because in some scenario where we are not careful about to apply load within the acceptable limit or within the I mean, if we apply too much load on the object that we might not be careful about or we might be ignorant about it, in that case, the wire might actually tear apart. And because this is a wire within tension, so if it ever becomes torn, this is gonna shoot itself like a whip. So we have to wear proper safety precautions. So wearing an apron is really good, but wearing safety glasses is a must so that you do not lose your eye just in case of any accident. So how this experiment works out, we have some wooden blocks over here for better clamping of the wire, or we can just use a G clamp over here that is with the ruler as well. And here we have a long ruler. The teacher for the video, he used two 1 meter rulers side by side to use a significantly long length of the specimen. Why do you need a long length? I'm gonna get to that part after a while. Try to understand. So we have the length of the wire clamped over here. And right on this side, we have attached the 0 centimeter mark of the meter rule over here. And this meter rule goes up from this part. And we have hanged this wire over the pulley this is a smooth pulley, considering that it has very low friction or theoretically zero friction. And then we have put the load over here, and this is the place where we're going to have the loads. There we have placed a cardboard box, which is called a mass catcher, just in case the wire actually becomes torn, so that the load can actually fall over here. Load doesn't damage our floor material like tiles or mosaic or whatever the material that is. So we need to have a cardboard box. So we can have a sand tray to catch the loads. Ideally, this is not necessary unless there is an accident, but this is usually given over here. So here's the catch. This entire wire is one single wire that eventually goes through here, but we are not going to consider the total length of the wire for our experimental procedure. There is a reason for this. The reason is that whenever we'll start to apply load onto this part, slowly this entire wire, starting from this end all the way over the pulley, all the way up to the hanging point over here, this entire wire will start to extend. So significant portion of the wire is going to slowly travel over the pulley and is going to follow downwards. If you want to consider the entire length, measuring the length can become very difficult, because in that case we have to observe in a curved surface. So we are not going to do that. What we are trying to do, we are placing a small piece of marker over here. This is actually a piece of page marker that usually looks like this. So this is a bit of a corner. So we glue this onto the wire, or we tape this onto the wire. The gluing force to the taping force really add very small resistance for the deformation. So we just do that over here. And this corner tip over here, the reason we have a corner tip over here, so that within the meter rule, let's say this is the meter rule, here is the millimeter marks of the meter rule. This corner tip can give us a very precise location for exactly what millimeter mark is the length representing it. And that's why we need a shape that looks like a bit like this, so that this corner can help us to measure the length very precisely. This is something that is called a marker. This is sometimes also used called the fiducial marker. Fiducial marker is just another fancy name that helps us to avoid parallax error in an experiment. So in this case, for this experiment, they have also used a traveling microscope for a better observation of this marker. But for US syllabus volume, the traveling microscope is actually not considered to be essential for this experiment. So we can, for the time, we consider this is not required. As long as you make sure that you are looking vertically on top of this wire and find out the perfect millimeter marking onto this scale, you are perfect to you're okay to go ahead with the experiment. Now, how does the experiment work? First, we set up the whole setup. We have these two paper flaps over here placed in two parts over here. We need to be a bit careful so the paper flaps don't touch the wire, so that not to introduce any friction. They're just going to be on top of this. We are using this as sort of like catching mechanism, just in case the wire breaks at any point. So for example, if the wire breaks over here, these two paper flaps are going to add some significant air resistance whenever it is trying to go out as a whip. So that way it will reduce the damage possibly it could possibly do for the experiment. So this picture is covered by Daniel Wilson. We thank him for this picture. It's a very good good picture with all the necessary equipment over here. So paper flaps are an additional precautionary setup for experiment, but it's not essential for the outcome of the experiment. So it was a primary situation. Then how do we do the experiment? First of all, we do not attach all the loads over here. We attach only a small piece of load at the beginning. Let's say we're going to only attach the small, very lower load over onto this setup. This is something that we are going to call the dead load. The purpose of the dead load is to make the wire taut, so that the wire is perfectly straight, and because of the straight wire, this is going to give us a fixed position of the marker onto this meter. So for our experiment, we're going to consider this much length that we get for this much dead load as our initial length, small l. Sometimes this is also represented as L naught. L naught represents the L at 0 force. So in this case, the variable factor is the force over here. So we're going to increase load over here, and by reading of the mass value from the load, we can actually convert that into weight, and that weight can be considered as the applied force onto the wire. So this is the force, which is a variable. Whenever we write L naught, it means this is the length of the L when 0 is the force. So for 0 force, we're considering the dead load to be a previously applied load within the wire, and we're considering for this to be not a part of our applied load for the specimen. This is a load that is applied just to make the wire taut enough. Now you might wonder, sir, if we are applying a load already, then isn't this causing a little bit of extension? The answer is yes, it is causing a little bit of extension, but we are considering that extension before our experiment starts. So this is the part that I wanted to understand. Let's say for a true wire, the force versus extension graph is like this. Whenever we apply the dead load, let's say of this much, then let's say it does this amount of extension. So this is becoming this point. We can very well choose to start our graph from this point. Our force and extension graph can also start from this point, and this is not going to give us any different graph than the earlier case. The gradient that we're going to have for starting from this point and the gradient we're going to have starting from this point are going to be exactly same. Don't you think? আমরা একটু পরের থেকে স্টার্ট করতেছি কেন? Because we want the wire to be perfectly taut for our experiment. Here comes another precaution that just popped in my head. সেটা হচ্ছে another precaution for this experiment, that before we attach the whole wire onto this setup, we must make sure that the wire is perfectly straight all through. So the wire should not have kinks or bends in its body, something of this sort. The wire should be made perfectly straight. And how do we make a perfectly straight wire? By usually pulling it across a sharp metal or wooden edge, and you have to just pull it. I showed you in your experiments sometimes. Did you do some physical experiments? No, there was no experiment, so I never showed it to you. But making the wire perfectly straight is a pretty simple process. Whenever physical class start, I might show you that it can be done very easily, but we have to be careful that this wire should be perfectly straight, because if we have bends and kinks like this, they are going to compromise the accuracy of our experiment. We don't want to do that. So up so far I have talked about 3 precautions: safety classes, paper flaps, no kinks over here, and there is another working precaution is that we're going to apply a bit of a dead load to make sure that the wire is perfectly taut. So when the wire is perfectly taut, we're going to take the reading of this meter rule, and this length starting from the 0 value over here is going to be our L naught. Then we're going to slowly start to add additional loads over here. So we're going to slowly start to load additional load. So we're going to apply one load, and then this thing is going to move a little bit to the right. So let's say in that scenario, this is the new position of the paper piece. So it's going to move a little bit to the right because this part of the wire is going to be elongated by a little bit, and we're going to take off this reading. So let's say this is our first extended length. So we're going to record this length value, which is happening for a combined load of this much. So we are never going to consider this green load. This green load is considered to be 0. This red load, the fresh load, is what we are considering to be causing the deformation, because this is the location where we are considering applied force is 0. This is the load where we are considering our first load. Let's say that is 100 gram. So that will be 0.1 g amount of Newton. This amount of force was applied. Then we're going to keep applying loads over here, go slowly, and this is going to slowly move to the right, and we're going to take a vertical observation to avoid parallax error and take the readings for all the individual values, which these values, when taken into a table, might look like this. So this is a sort of a table that we can have. Let's say this is number of observation, and then we can write that how much mass are we applying over here, which can give us how much force are we applying. This is the extension, which is going to be equals to L minus L naught, and then we can calculate the sigma, which is going to be in Newton per meter square. This is going to be in Newton. This is going to be in meter. Mass is going to be in maybe gram. And then we can also calculate the strain, which is delta. Delta doesn't have any unit, so I'm not writing in unit. So let's say the first observation that we're going to do is our observation number 1, where we have applied 0 mass. So this is our default observation. So we have 0 force applied, and the length that we're going to, and we have 0 extension over here. This is basically representing that we have the original length. So actually this is not very good. I should not do that. So we should, before we start the experiment, we should record the L naught of the experiment. So what is the length of this thing over here before we introduce the first applied load, and we're going to record this at some place. And also one more thing, if you're trying to calculate the sigma over here, have a look. Sigma is given by what? Force over area, cross-sectional area. So to calculate this stress value, we have to have a number for cross-sectional area for our requirement. So how do we calculate that? The process of cross-sectional area is that before we set up the wire within our contraption, or before we actually attach the wire within this thing, we should use the micrometer screw gauge to measure the diameter of this wire in multiple different locations. So we should take at least 3 diameter readings. Taking 5 is very much recommended. Taking more than 5 can prove to be time consuming, so we better not do that. It's very important to care for the zero error in your micrometer screw gauge whenever you're using a micrometer screw gauge, so that you do not make a mess up the reading. So we take the measurement of diameter in multiple places. Then using the diameter measurement, average diameter, we calculate the cross-sectional area in a defined location. And we're going to use that value of cross-sectional area for throughout our case. We're not going to use different values of cross-sectional area. So we're going to measure the diameter in different places for an ideal where the diameter is supposed to be same everywhere. But for many cases, because of the diameter might not be exactly the same, there can be a little bit of fractional differences here and there. That's why we prefer to do the average, and we can calculate the cross-sectional area. So the original length should be recorded somewhere else. The cross-sectional area should be calculated and recorded somewhere else before the experiment actually gets started. Then if we apply, let's say 100 gram mass, the total amount of force is gonna be 0.1 into 9.81, that is 0.981 Newton. That is the amount of force in Newton. So for 100 gram mass, the applied force is gonna be 0.981 Newton. So the extension is gonna be the new length minus the original length. So whatever that value that you get, you write that into meter. Then you place the calculated value of stress over here, place the strain value over here. Then you keep doing this observation for multiple different times. Now there is a catch. Acha, before I go for the catch, এই পর্যন্ত প্রসিডিউরটা বুঝা গেছে কিনা? বলবান।
Yes, sir.
সো আমরা একটা একটা করে লোড দিব, আমাদের মার্কারটা একটু একটু করে শুরু, আমরা একটু একটু করে রিডিং গুলো নিব। সো এটা ইউজুয়ালি এভাবে এক্সপ্লেইন করলে হয়ে যায়, বাট দেয়ার ইজ এ additional precaution for the sake of available opportunity and also for the sake of a better doing the experiment. সেটা হচ্ছে, in many cases it is recommended that we should take an average of the length reading while loading and while unloading. So we might also choose to have one more row over here. So what I'm trying to propose is something like this. Let me write a different table. It's the same table but with one extra column. So let's say this is our number of observation. We have the mass in gram. We have the force calculated in Newton. We have the length of the spring while loading. We have the length of the wear while unloading. Both of them should be given in, let's say, meter. So I should not forget the unit meter. And then we should have the average length average in meter. And then comes the extension, which is length average minus original length, which should be also in meter. So let me tell you what this actually means. This actually means that this is actually a recommended method that other than using only one set of data, we should do the observation of this fiducial marker that is going to move over the length of the meter roll while we are applying the load in one go. And then as we're going to remove the loads from the object, we should also do the observation one more time. What it means, mone koro, let's say we're going to do this experiment for up to maybe 1 kg. So let's say we're going to apply 100, 200, 300, 400, 500, 600, 700. Achha, maybe we're going to do up to 800. Let's not go too much. So let's say we're going to do up to 800 grams. So the recommended method over here is that once we do up to 800 grams, we're going to have only one reading because this is our last reading. So this is not going to be, we're not going to have any unloading level. Whenever, so this would actually mean what? Whenever we have 800 grams, let's say this is our hook. Over in the hook, at the very bottom, we have the dead load. So this might be of something which we are not going to bother. So then over here, these are 100, 200, 300, 400, 500, 600, 700, 800. So let's say there are 8 different loads over here. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the scenario for our last reading. So when we were loading the loads, whenever we were increasing the length, increasing the mass, then we got one value up to the 700 gram. Now, if I just take off the 800 gram off over here, what's going to happen? We're going to have the total load up to the 700 gram once again. ঠিক না? এই যে বুঝতেছো? As we unload means as we remove the deforming force, if we take off the 100 gram, the total amount of load over here is going to be once again 700 grams. So what is recommended? We should once again take another length of the reading on the fiducial marker for the 700 grams. So 700 gram is going to have one length value over here for the loading case and the value over here for the unloading case. Now you might wonder, for within the elastic limit, these two lengths are supposed to be very much equal. This is absolutely true. For an ideal case scenario, they are not supposed to be different, but in some specimen, in some experiment, they can prove to be different. If this applied force over here, it has somehow surpassed the elastic limit, then we're going to have different lengths over here. This is a helpful precaution to convince us that we did our experiment within the straight line part of the graph. If these two lengths are, if these two measurements are exactly same, or they're very much within close approximity to, for example, you might have 0.1 centimeter difference or 0.2 centimeter difference, that can be considered as a observation error per se. But if you have significantly large difference, then you should understand that whenever we are applying this much load, at some point over here, we went over the elastic limit. That's why these two lengths are not perfectly agreeing with each other. So it's important that we do both of these things. And as long as both of these lengths are pretty much same or exactly same, we're perfectly covered. So that's what we're going to do for all the upcoming loads. So we're going to do this for 600 as well. So we're going to have 2 readings over here. For 500, we're going to have 2 readings over here. So while loading, we're going to record these things. While unloading, we're going to record these lengths all together, and we're going to find out the average over here. And then using the average value, we're going to find out the actual extension. Do you understand this part? The loading and the unloading observation? Ulaban?
Yes, sir.
বুঝো নাই কেউ আসো?
আমি আসি স্যার।
আচ্ছা, মুনাম কোন পার্টটা বুঝে নাই বলো?
এই তো লাস্টে যে কি বললেন এগুলো কিছু বুঝতেছিলাম না।
লাস্টে মানে কোন জায়গা থেকে?
কেমনে বলি স্যার? আচ্ছা স্যার, রেকর্ডিং দেখে নিব না, সমস্যা নাই, আপনি ক্লাস করান।
আচ্ছা ঠিক আছে, তুমি যদি পরে ডিফাইন করতে পারো বা আমাকে মেসেজে নক করে আমি তোমার পরে বুঝিয়ে দেব, সমস্যা নাই, নো বিগ ডিল। So that's how we should have the total set of reading, one for the loading and for the unloading. I mean, taking 2 set of readings for while loading and unloading is actually a bit of a precaution. This is important so that we make sure that our applied load did not go over the elastic limit. So this is pretty much it. Precautions, we have already said we should have a mask catcher. We should definitely wear safety goggles. We can also use some paper flaps on the wire so that if it ever becomes torn because of too much loading of weight over here, the wire does not shoot itself too much high or doesn't damage ourselves. That's pretty much it. তোমাদের বইতে এক্সপেরিমেন্টটা খুব ভালো করে মনে হয় দেওয়াও আছে। আমার কাছে বই আছে হচ্ছে কোনটা জানো? পুরানটা আছে আমার কাছে, দাঁড়াও, কোথাও যেন হেল্প ম্যাটেরিয়ালস নামে একটা বই আছে। তোমাদের বই জানি কোনটা? আমার কাছে সেকেন্ড এডিশন আছে। এটা কি নতুন কোন এডিশন বের হইছে না এখনো সেকেন্ড এডিশনই চলতেছে?
না স্যার, নতুন বের হচ্ছে স্যার।
হ্যাঁ
স্যার, ভায়োলেট কালার।
স্যার এই এডিশনটা সেট তো দিয়ে দিবেন গ্রুপে স্যার।
আচ্ছা ঠিক আছে, সমস্যা নাই।
স্যার এটা আমাদের ল্যাবে করতে হয়, ইয়াং মডুলাস।
হ্যাঁ, এটা ল্যাবে করতে হবে। It's a pretty simple experiment, but it's time consuming. হ্যাঁ, ইয়া কি বলছো?
এরকম মাইক্রোস্কোপ কি আছে স্যার?
হ্যাঁ, ট্যাবলেট মাইক্রোস্কোপ আছে। Actually, sometimes we also prefer to use the Sarlis equipment. Sarlis equipment is also another way to measure this experiment very precisely, which can have a built-in micrometer screw gauge within itself. So Sarlis apparatus তোমাদের সিলেবাসে নাই দেখে আমি তোমাদেরকে পড়াচ্ছি না, but if you're interested, I can help you understand that thing in times other than the class time duration. So এটা হচ্ছে আমাদের সেই এক্সপেরিমেন্টের সিনারিও, matters and materials যেগুলো সব মোশন, we have it in a continuous part, then we have this thing এই যে। সো আগের বইতে এটা আছে হচ্ছে তোমাদের পেজ নাম্বার 105 এ, যে এখানে দেখো এই যে আমাদের সেই অ্যাপারেটাসটা দেখানো আছে। So we have this meter rule, we have the clamp, we have the pulley, we have the wire load with the sticky tape pointer, which is basically the fiducial marker, and then we should take this, taking the wire in the laboratory, wear eye protection and be careful not to overload the wire. This is very important for this experiment. So If Hooke's law is obeyed within the linear region, then we should have a perfectly straight line. That's what we make sure by taking readings while loading and unloading both. আর যদি আমরা এই রিজনের বাইরে চলে যাই তখন আমাদের গ্রাফটা কার্ভ হওয়া শুরু করবে. That is something that we want to avoid. And then eventually we draw up the graph and we measure the gradient of the straight line part of the graph. That basically gives us the measure of the Young's modulus for the material of the specimen. So that's pretty much it. So we have some distribution over here. So it's also pretty simple. আচ্ছা, এটা গেল হচ্ছে আমাদের experiment. Now I'm gonna start to describe about the different parts of the stress strain graph that we can have depending upon different shapes. So let me find out a suitable figure. Okay. Let's go for this one. This is actually a bit more theoretically accurate. Okay, let's try to understand what is happening over here. Have a look. What we've learned up to our O-levels point, O-levels part, that is within the limit of proportionality or elastic limit, we have learned both of these things to be exactly same. But in proper experiment or in minute experimental procedure, what we have found out that the limit of proportionality and the elastic point of an object, they happen to be not the same point. They are not the same point. What do I mean by this? Whenever experiment is done for force versus extension, and actually we apply the load onto the object and then we remove the load once again, the object is allowed to come back to its original length, and then this is actually the process to determine whether the object behaves elastically or not. So what I'm trying to mean is that, let's say we're going to do the same experiment over here. We're going to apply, let's say, 100 gram load and we're going to take a measurement of the length, and then we're going to remove the 100 gram load and allow the string to come back to its original length to see whether it was within the elastic limit or not. If it does come to the elastic limit, well and good. Then we're going to apply 200, do the same thing and remove the whole load and observe whether it comes back or not. So we can do this thing multiple times. It's going to be a time-consuming experiment, which is perfectly all right. But we can do this thing, and eventually we can come up with the stress-strain graph for the whole region. So there are certain locations where the graph starts to take a curve. This is the interesting part. The actual graph that we get for a stress-strain graph has a shape that looks somewhat like this. So you can see over here, this is a stress axis, this is a strain axis. We're starting from 0, and up to this much point, up to a point, we have a perfectly straight line. So A is the end point of the linear part of the graph. Try to understand, this is a geometric property of the graph, straight line. A point take আমরা বলতেছি proportionality limit. We're calling this A as the proportionality limit or limit of proportionality, which means till the graph is a perfectly straight line, that is what we're calling a proportionality limit. It just so happens that any elastic object behaves as an elastic object. Elastic object means its deformation is reversible slightly inside the curve as well. So it means from this point, let me use maybe red, from this point all the way up to this much point, this is actually a curve. This is not a straight line. But even within this curve, the deformation would still be reversible. It means if an object is loaded up to this much stress and the entire load is removed, the object is capable to come back to its original length. And that behavior is observed all the way up to this much stress value or up to this much point of the graph. So this much part of the graph is not a straight line, but it is still elastic. This is definitely elastic because this is a perfectly straight line. It means what? That the amount of deformation and applied force are perfectly equal. So what you need to understand, proportionality limit is the end point of the straight line part of the graph, which is a geometric property. যেখানে গিয়ে আমাদের straight লাইনটা কার্ভ হওয়া শুরু করছে সেটা হচ্ছে proportionality limit or limit of proportionality. Whereas elastic limit is a physical property based point. Physical property based point means up till the point of the graph, the wire behaves to give us a reversible deformation. Up to the point of the graph, the wire behaves to give us reversible deformation. Reversible deformation means that if we remove the applied load, the specimen essentially comes back to the original dimension. So that is what we're defining as elastic limit or yield point. So ওই পয়েন্টটা কার্ভের মধ্যে, বাট আমাদের এইটুক বিহেভিয়ার মানে হচ্ছে এইটুক রিজিয়ন হচ্ছে ইলাস্টিক রিজিয়ন, আর এটা পরের থেকে ফার্দার টু দ্য রাইট all the way up to here, this is what we call the plastic region. Plastic region means that object will not behave elastically. Object will have some permanent deformation stuck within itself, which means object will have some permanent deformation. And permanent deformation কেন মেজার করব সেটা আমি আরেকটা ডিফারেন্ট ভাবে দেখাচ্ছি, বাট এই দুটো পয়েন্টের ডিফারেন্সটা বোঝা গেছে কিনা? Do you understand properly the difference between limit of proportionality and elastic limit? Does it make sense so far? Palaban?
Yes, sir.
Yes, sir.
আচ্ছা, এখানে let me paste it once again. একটা জিনিস খেয়াল করো, what you can see, so this is actually a wire, this is actually a diagram for a metallic substance which actually has a large plastic region. Large plastic region means that it can undergo a very huge amount of plastic deformation or permanent deformation for a significantly large amount of load. So this was the point up till which the object was behaving elastically. This is the elastic stress. This is the stress within which the elastic behavior was acceptable. Elastic stress is not a term, forget about that, I mispronounced that. And this is the maximum amount of stress the object can take. So this is the point which is U. This is called the ultimate tensile stress or UTS point. Ultimate tensile stress or ultimate tensile strain point, however it's said. This is the point which is the maximum y-axis point or highest point on the stress strain graph of an object. It means the object can withstand up to this much amount of stress maximum. Beyond this point, the object is gonna go towards breaking. এই পয়েন্টের পরের থেকে আমাদের স্টার্ট হয়ে হচ্ছে নেকিং, নেকিং কি জিনিস সেটা আমি তোমাদেরকে ভালো করে বুঝাচ্ছি। So the way it's going to work out is that if we extend the object, before I get into this part, in all of these graphs you're going to actually come across to see there is a certain point that labeled as C. What is this C point? C point actually does not have much of a significant name-based importance. This is just representing a simple point that is within the plastic region of the graph. Now here is the catch. মনে করো আমি একটা জিনিস তোমাদেরকে বুঝাই। Let's say this is a metallic rod. Okay, we want to bend this rod at this location. How do we do that? We clamp this part over here. This is a strong clamp. We provided a pivot support over here, strong support. Then we apply some load over here that can move around. So if we apply this load in a circular pattern like this, we can make this rod bend in a shape like that. ঠিক না? Do you understand my point? আমি কি দেখাচ্ছি এটা বুঝছো? If you want to bend a rod at a certain point, this is how we can do this thing. Now here's the catch. If we remove this applied force and the object retains this shape, it means the object has undergone some permanent deformation. Within this part, there was permanent dislocation of the existing metal atoms so that it now has a different shape than earlier. Earlier, the object was perfectly straight. Now the object is bent around this point as a curvature. Even when the object is done or bent to its to a permanent deformation, the object is still the same material. This is a part that I need you to understand. Before we introduce the permanent deformation, it was, let's say it was made from iron. After the deformation, it is still made up with iron, which brings us to understand that this material is going to behave under the same value of Young's modulus whenever it can. The object is going to behave with the same value of Young's modulus whenever it can. Let me illustrate what it means. Let's say within the stress strain graph, so what happens? Let's say this is our limit of proportionality. So I'm going to label this as P. Let's say this is our elastic limit. Let's say this is the point labeled as E. তার মানে হচ্ছে এইটুকু হচ্ছে আমাদের elastic segment. This is the part of the deformation or strain that is elastic. Anything beyond this point, these are all plastic deformation. Now here's the catch. The highest point on the stress strain graph is what we call the UTS point, or the ultimate tensile stress. This is the maximum amount of stress that specimen can withstand. Beyond this point, what we have started on the specimen is called necking, and from this point, the object can have multiple different breaking behavior. So you can see over here, I've drawn one straight line over here, multiple different dotted lines over here, because the object can follow different paths from this point onwards, even though they are all taken from the same sample. Here's what I mean. Let's say there is a long piece of rod that was manufactured in a manufactured plant. You are trying to find out the total stress strain graph of this rod for 4 different specimens up all the way up to the breaking point. So let's say we are going to cut this into 4 pieces, load it up in an apparatus setup, and you are going to do this experiment onto these individual 4 pieces all the way up to the point it actually breaks. What is going to be interesting that all of these 4 pieces, the pieces can be big or small, doesn't matter. They're going to end up with the same exact graph all the way up to the UTS point. A point পর্যন্ত সবার graph exactly same হবে. But from this point beyond, you can have different lines of graph all the way up to the breaking. This cross line represents breaking, that the object has actually broken into 2 pieces, can no longer be loaded. It has been destroyed. Now, why could that happen? These were all manufactured in a single plant, in a single process, and you actually simply cut them off into 4 pieces, but they have different graphs. Why? Because of necking. Let me explain what necking is. Necking basically means something that looks like a neck. How does the human neck looks like? Here is the head, here is the neck, and here is the body. Figure not down to scale. Okay, this is the stomach, this is the body. So stomach is big. So let's say this is the human being. So necking basically means whenever you have a significantly thin portion between 2 large portions. That's basically what it means by necking. Let me help you understand what this actually means in metallurgical sense. No, this is not the necking that we're talking about. We're talking about this necking. This is what we mean by necking. Acha. I'll show you some video regarding necking. I shouldn't say typically.
thumbnail এটা চলে আসছে স্যার
Yes. Okay. Okay. So let's have a look at this experiment, and I can explain the idea of necking through this video.
The tensile.
The second the same graph as the first one because of the metallurgical property within the specimen. So one object, multiple different objects behave differently depending upon what is the type of metallic bonds that they have at a macroscopic level. For example, the first one was a high carbon steel. Sorry, mild steel, not high carbon steel. The first specimen was mild steel, and the second specimen was precipitated aluminum rod. So they have different type of metallic bond within themselves. That's why we have that kind of a difference. Taki ki jono boltesila?
স্যার ওই যে ফার্স্ট গ্রাফে স্যার মাঝখান থেকে জিগজ্যাগ প্যাটার্নটা ওর পার্ট আমি বুঝি নাই স্যার
ওই পার্টটা হচ্ছে this is what we call আচ্ছা আমি বলতেছি that part is usually existing between the limit of proportionality and the elastic limit. So certain materials give us a graph that looks like this. It goes up like that, and then it comes down and gives us a bit of a zigzag shape like this, and then it starts to rise up from there to give us this curve, and eventually it falls down like that. So তোমাদের সিলেবাসের এই পার্টটুকুকে হাইলাইট করা হয় নাই. The way your syllabus graphs are prescribed for the sake of simplicity is like this. বুঝছো কি বলছে?
মানে স্যার আমাদের শুধু যে ইলাস্টিক প্লাস্টিক নেকিং এটাই
Exactly. Limit of proportionality, elastic point, UTS, breaking. এর মধ্যে এটুকু হচ্ছে সরি ইলাস্টিক লিমিটের আগ পর্যন্ত হচ্ছে ইলাস্টিক ডিফরমেশন, এটুকু হচ্ছে প্লাস্টিক ডিফরমেশন, আর হচ্ছে এখান থেকে এটুকু হচ্ছে নেকিং, এইটুকু পার্টের মধ্যে হবে নেকিং. নেকিংটা হচ্ছে the idea of necking is that whenever as we deform the whole object, for example, if you have a look at the picture of a necking, দাঁড়াও দেখাই. এই যে So for example, let's say we are elongating a certain object under stress, under tensile stress. So beyond up to a certain point of application of force, the object is going to keep on deforming uniformly. So this was a large specimen, this is a bit thinner specimen, and you can see that the diameter has reduced uniformly. But there would come a certain point when the object will start to deform at a very specific point within its body. It doesn't essentially have to be exactly at the middle. It could happen anywhere. But once it starts to happen, what I need you to understand, let me just copy this image. What I need you to understand that once the neck gets developed, so let's say we have the neck developed right over here. What you should see, a point আমাদের একটা cross sectional area আছে, এই পয়েন্ট আমাদের একটা lower cross sectional area আছে, and stress এর formula কি? Stress is given by F over area, তাই না? বুঝো, stress is given by F over area and Young's modulus is given by stress over strain. তার মানে হচ্ছে আমি যদি এখান থেকে যদি স্ট্রেস কে সাবজেক্টে I'm going to get y into strain. তার মানে y হচ্ছে বেসিক্যালি একটা ম্যাটেরিয়ালের কনস্ট্যান্ট. Young's modulus is a material constant, which basically means that the stress will be directly proportional to strain at any given stage. তার মানে যেখানে স্ট্রেস যত বেশি হবে সেখানকার ডিফর্মেশন তত কি হবে, ন্যাচারালি তত বেশি হবে। এখন তুমি দেখো স্ট্রেসের ফর্মুলা হচ্ছে ফোর্স ওভার এরিয়া। একটা জিনিস খেয়াল করো, যখনই নেকিংটা ডেভেলপ হলো এই জায়গায় ক্রস সেকশনাল এরিয়া আশেপাশের রিজিয়ন থেকে সিগনিফিকেন্টলি কমে গেল না? But you have to understand that the applied force on both direction is exactly same in both directions. We have the same force applying on all the sections of the object, but the cross section area is exclusively smaller over here, which means the biggest amount of strain or biggest amount of stress would be developed exactly at this section. ঠিক না? I mean, if you consider the force, that is same everywhere, but because of the difference of cross sectional area, the strain is not same everywhere. Over the uniform cross sectional area region, we have the same strain for every section, but over here we have a much bigger stress. Bigger stress means the strain over here will be even bigger, which means now as the object keeps on elongating, this part would pretty much remain undeformed, whether the object is gonna keep on deforming over this much part exclusively. And this is gonna start to make the neck bigger and bigger, and ultimately the object is gonna crack somewhere over here. বুঝছো কি বলছি?
জি
মানে নেকটা ডেভেলপ হয় not necessarily exactly the middle হবে, উপরে হতে পারে, একটু নিচে হতে পারে, but within the specimen the neck will be developed. But once the neck is developed, the object is going to crack exactly at the neck position, because within the neck position the cross-sectional area of the specimen is very small, which leads to a much bigger stress, ultimately causing in a much bigger strain. So the deformation of the object after the necking gets limited within the region of the necking. বুঝা গেছে?
জি স্যার।
ঠিক আছে। সো এই জিনিসটা হচ্ছে আমাদের এই গ্রাফের বেসিক আইডিয়া, যে কারণে because different specimen can have different location of necking, that's why we can have different dot lines coming up for identical specimens that we started with. So even if we start with identical material, we can actually come across the same type of graph over here, but this dropping part of the graph can be slightly different for apparently identical looking specimen, because at atomic level nothing is absolutely comparable, nothing is absolutely identical. So it is possible that I mean, what I need you to understand, তো আমরা যদি আমরা মনে করো একটা অবজেক্ট দেখতে পারফেক্টলি রেক্ট্যাঙ্গল, আমি শেষ করতেছি হাসান, জাস্ট গিভ মি লিটল বিট টাইম। মনে করো একটা অবজেক্ট দেখতে পারফেক্টলি রেক্ট্যাঙ্গল, হয় নাই, মনে করো একটা অবজেক্ট দেখতে পারফেক্টলি রেক্ট্যাঙ্গল, কি ব্যাপার এখানে ইনটু শেপ অন করা নাই? অন করা নাই, আচ্ছা।
ট্রাপিজিয়াম হইছে,
লাখ খারাপ।
হ্যাঁ হয়েছে। মনে করো একটা অবজেক্ট দেখতে পারফেক্টলি রেক্ট্যাঙ্গল, এটাকে আমরা খুব পারফেক্টলি অ্যাটেম্প করে এফোর্ট দিয়ে রেক্ট্যাঙ্গল করছি, বাট ইফ ইউ হ্যাভ এ ভেরি গুড ম্যাক্রোস্কোপিক লুক at the surface level over here, macroscopic look that I'm saying, this is definitely going to appear to have some amount of ups and downs. And on the opposite side as well, if you take a good microscopic look over here, you're going to have some ups and downs. What I'm trying to mean over here is that the precise value of cross-sectional area between levels, they are not exactly same. There's always going to be some amount of variation for the exact value of cross-sectional areas. Now,
yes,
that
sir.
slight variation of cross-sectional area does not pose a significant effect on the deformation within this much point. So এই পর্যন্ত সেই পুরো অবজেক্টটা ইউনিফর্মলি ডিফর্ম হয়, ফর এক্সাম্পল ফ্রম হিয়ার টু হিয়ার, But beyond the UTS point, the locations where you have the smallest cross section area start to experience a very significant amount of deformation, and those are the points where you can have the neck developing. So that's the reason different specimen can have necking showing up by different amount. মনে করো হচ্ছে এই ডিফারেন্সটা যাদের মধ্যে একটু বেশি ছিল তারা অনেক কম ফোর্সেই ব্রেকডাউন হবে, যাদের মধ্যে আর2 কম ছিল তারা আর2 বেশি ফোর্স পর্যন্ত বেশি ডিফর্মেশন পর্যন্ত উইথস্ট্যান্ড করতে পারবে। সো ইউ ক্যান হ্যাভ ডিফারেন্ট ব্রেকিং বিহেভিয়ার from apparently similar looking specimen because of the microscopic level difference of their surface properties. বুঝছো কি বলছি?
Yes, sir.
Everyone else?
Yes, sir.
আচ্ছা ঠিক আছে, আজকে এই পর্যন্ত থাক। তোমার নেক্সট ক্লাসে কালকে পারলে ওয়ার্কশিটগুলো কালেক্ট করো, টিউজডেতে পারলে আমি তোমাদের কিছু ম্যাথস করাবো, সমস্যা নাই। আসসালামু আলাইকুম।
Sir,
বলো।
sir, আমাদের কি টপিক মক হবে স্যার?
হ্যাঁ, টপিক মক নিব। টপিক মক হবে 1 মাস।
স্যার কবে শুরু হবে স্যার?
টপিক্যাল তোমার এই কোর্সের মধ্যে ক্লাসেস গুলো দিতে থাকবা, সেটা সমস্যা নাই। আর হচ্ছে টপিক্যাল মক হবে হচ্ছে জানুয়ারি মাস ফুল 1 মাস, আর ফুল সিলেবাস মক মানে ওই সিএস সিস্টেম মক হবে হচ্ছে ফেব্রুয়ারি মার্চ এপ্রিল 3 মাস।
স্যার ক্লাস টেস্টটা কবে নেবেন স্যার ইয়েতে?
ক্লাসেস কপিগুলো তোমার কালকে কালেক্ট করতে পারবা তোমাদের ইয়ার কপির সাথে, কিসের এই বুকলেট 2 এর সাথে।
কোন
এক্সাম
চ্যাপ্টার
যে
উপর
কোনো
দিয়েছিলেন
সময়
স্যার?
দিতে পারবো।
ফার্স্ট চ্যাপ্টার, প্রথম চার
ওকে
চ্যাপ্টার।
স্যার।
ওটা সাবমিট করে
চারটা
ওই মকে যে সময় সাবমিট করতা আমাদের সেকেন্ড মেসেঞ্জার অ্যাকাউন্ট, ওটা আমি ওটা প্রসিডিউর বলে দিব না, সমস্যা নাই, ডোন্ট ওয়ারি।
জি স্যার।
আচ্ছা, আসসালামু
আল্লাহ
আলাইকুম।
হাফেজ স্যার।